So let's look at some of these Hardy-Weinberg questions.
Sir, can you give me a second? The laptop to be thinking about loading.
Ranja, I'm recording this stuff.
No, I know.
So just thanks. All right, so let's look at. So your quiz is going to be 2 questions. One will be straightforward. The other one not so much. Okay. So a straightforward question would be something like 1, where we're asked for.
If not straightforward, is 2 that I should do.
No, 2 is minor league. So, cystic fibrosis. Now, you got to remember your genetics, okay? So, cystic fibrosis. So, here's the thing. Don't ask me on the quiz if it's recessive or not, okay? Because that's actually part of the Hardy-Weinberg is being able to logically determine which allele to use. So, if I tell you, I'm giving you already information, and your job is to figure that out. Yep. There's only going to be a few. If it's something that we haven't talked about, then I got to give you some more information, right? But so we've talked about cystic fibrosis.
Sir, let's see its color. Do you assume like red and white juice, or like dark and light? Do you assume that light is recessive?
No, you can't assume that.
Then you would give it.
Yeah. If it's something that you don't know, I have to give it to you. So like this one we know. We know cystic fibrosis is recessive. So we know for you to get cystic fibrosis, you need 2 copies of it. What allele represents the recessive one? Q. So Q squared is someone who has cystic fibrosis, right? Because you need 2 copies to get the disease. If you have 1 copy, you're heterozygote, you're still okay. So we got to work off the homozygous recessive, right? So Q squared is, in this case, we have 4 have the disease out of 10,000. We take the square root of this, so that should be 2 out of 100. Should be 0.02. Okay? So 2%. The allele is 2% in the population. Okay? So you work with the recessive.
Wait.
That's it. Question asks you for the frequency of the cystic fibrosis allele, which we know is recessive, and we know that in Hardy-Weinberg, the Q represents the recessive allele, but you need 2 Qs to get the disease, and 2 Qs is the same as Q squared. Okay? You don't do the Punnett square. You don't need to. Now, this question is very similar. Okay. Now, this one we talked about. This is the peppered moth. This is the one on the tree. So in this case, light is recessive. So the light allele is Q. So if you're going to be a light colored moth, you need 2 recessive alleles. So Q squared is the light phenotype. Okay? The dark allele is the P allele. You only need 1 copy. So we have 2 samples, okay? So here we have a forest. Okay, here's my little forest. And it says, in a forest upwind from an industrial center. So here's my industrial center. Okay, it's got some smoke. Alright. Now, upwind and downwind. So downwind would be, so let's say the wind is going this way, and I have a forest on either side. Downwind is in the direction of the wind. Upwind is the opposite direction. So this is upwind. This is downwind. So the smoke is going to go with the wind. So we expect that these trees would be slightly darker than these ones. So let's see. In the area that's upwind, We have 85 are dark. So on the upwind part, we have 85 are dark, but we don't use that. We don't want the information for the dominant one, we want the recessive one. So if you have 500 mods, that means 415 are what? Lights. And that's what we use, because we know that Q squared is the light allele. Sorry, Q squared is the light genotype, but we can figure out what Q is. So again, we did the same thing. We figure out what Q is. Okay, so what's Q? 0. What? 0.91. Now, if we look at, that's upwind. Okay? If we look at downwind, we have a different set of numbers here. It says 210 are dark. Now we caught 300 moths, and 210 were dark. So how many were lights? 90. 90 are lights. How many did we capture? 300. So 90 out of 300 are lights. We know that light is Q squared. So we do the exact same thing to figure out what Q is. What's Q in this case? 0.55. Now, so in the downwind section, the allele frequency, so on this side, is 55% light. In the upwind, it's 91%. Now, does that make sense? Because in C, it asks you for a possible reason. What would the possible reason be? So remember, if it's not in equilibrium, if it's in equilibrium, we expect numbers to be what? The same. It looks like the numbers are not the same. So something's going on. What are the 5 assumptions? Well, it's small population, so maybe numbers drift, right? Could be just randomness. But probably here, I would imagine they give you information about the forest and the wind and the factories. What do you think? Well, they didn't say factory, but industrial center. Yeah. Right. Because if you're a lighter moth on a darker tree, you have a higher risk of being what? Eaten. So then you would expect the numbers to go down. And that's what you see. Okay? Alright. I'm going to skip 3 and 4. We have the, actually, I'm not going to skip, I'll skip 3. We have the solution for 3. No, I'm not going to do all of them, okay? Because the solution is there. We can go over it at some other point. But I will explain 4. Okay? Because 4 is a scenario where it's not so straightforward. Right? So let's take a look at 4. So we have an allele, dominant H is 0.65, and we have 10,000 individuals. So the dominant allele, so here they're using H, but H would be then what allele? H would be the same as P, right? So P would be 0.65, because P is the dominant allele, and Q would be what? 0.35, because they have to add up to 1. Now, we can go ahead and figure out what the genotypes are. So P squared would be 0.65 squared. So P squared would be 0.65 squared. So what would that be? What's 0.65 squared? Should be probably like 40 something percent. 0.4 something, I would think. 0.42. Okay. What's Q squared? Q squared is 0.35 squared. So Q squared must be what? probably close to 1, I mean 0.1, 0.12. Now, these two add up to 0.54. That's 54%. You could calculate this two ways. You could say 2 times P, 0.65, or times Q, 0.2. Or you can just say, look, this and this and this have to add up to 1. So if these two are 54%, this must be 46%. You might get a slightly different answer if you do it that way than if you actually calculate it because of the way you round it off. But your numbers should be very close. Okay? And I don't care which way you do it on your quiz or test. Now, it says that the homozygous recessive is sterile. So we've done a scenario like this, right? That means that they can't have babies. So if we were to translate this into actually individuals, 42% of my population would be how many people? I have 10,000 people. You would expect that that would be 4,200, right? So this is 4,200 individuals. Because it's just the frequency times the actual population. This would be 4,600 individuals. This would be 1,200 individuals. Because we have 10,000 in total. Who can't have babies? Right. But we have 4,200 individuals with 2 P alleles. And we have 4,600 individuals with 1 P allele. So they have 2 P alleles each. They have 1 P allele. In total, only 8,800 individuals can reproduce. And we know they each have 2 alleles. So that would be 17,600 alleles that can get to the, potentially get into the, well, half of them, but that's the total number of alleles that you have. So how many of those are P alleles? Well, this is 8,400, and this is another 4,600. So that would be what proportion for P? What's the frequency for P? So 8,400 and 4,600 is 13,000. So 13,000 out of 17,600. What is that as a percentage? Or a frequency? You can do this as a frequency. What is it? Okay, 0.74. So this is 0.74. Now, do you expect it to go up? Yeah, because a lot of the Q alleles can't get to the next generation. So if a lot of the Q alleles can't get to the next generation, it increases the odds of the P allele. So if this is 0.74, this must be 0.26. And then we can go ahead and figure out the other stuff. We know that P squared is 0.74 squared. So 0.74 squared, what would that be? And we can figure out Q squared, because we know it's 0.26 squared. So what's P squared? Should be over 50%. Point what? 55. So 0.55. This should be less than 10%. What's 0.26 squared? 0.07. That adds up to 62%, so we're missing 38%. So then 2PQ must be 38. If you want to do for the following generation, you do the exact same thing. You can assume 10,000 individuals and then break them down into how many are P squared, how many are 2PQ, and how many are Q squared. Okay? Questions? No? Alright. In some populations around the world, the allele frequency for sickle cell is 15%. If we have 35,600, how many would have the disease? So, what is the sickle cell? It's recessive, right? Sickle cell. It's recessive. So how many copies do you need to get it? So you have to be Q squared to get sickle cell, right? So the allele frequency is 15%. But we want to know how many are Q squared. Well, that will just simply be, if Q is 15%, Q squared has to be 0.15 times, squared, right? So what would that be? Q squared. We know what Q, they're telling you the allele frequency is 15%. So they're telling you what Q is. You got to figure out what Q squared is, because to have the disease, you need 2 copies. Because it's recessive. 0.02. So that's 2%, right? So 2% have the disease. Now here we want to know how many. If I have a population that is 35,600, how many have the disease? Well, 2% of 35,600 would have the disease, right? So mathematically, that would be 2%, which we know 2% is 0.02, times the actual population size, which is less than 1,000. I'm going to guess 700. What is it, 700 what? Seriously? It's 35,600 though. Yeah, so it should be 7,000, 700. And what's 2% of 600? 12, 712. So 712 is these. Okay. Yeah, that's it. Number 6, we have, we have another recessive condition called iron overload. I only taught myself to say that. I kept saying overlord, but it's overload. So what happened? Now, what's the role? I know, I probably will say overlord. Why do we need iron? I'll be quiet. Why do we need iron?
Because iron is important to our body.
Thank you, but why? Not for your bones. Yep. Yes. It's so your blood has to make a protein called hemoglobin. We talked about abnormal hemoglobin with sickle cell, but if you don't have enough iron, you can't make the hemoglobin. So anemia, that's different. Anemia is a condition where you cannot carry enough oxygen. Now, if you have sickle cell anemia, you can't carry enough oxygen because the red blood cells don't move very well. Yes. If you don't have enough iron, you can't make enough hemoglobin, so you can't carry oxygen. This is a different type of anemia, okay? Now, it's recessive. This condition is the opposite of having not enough iron. This is having too much iron. Too much iron is actually not good for you either. Okay? A lot of infectious agents love iron, and they multiply like crazy when there's a lot of iron, and that's not good for the individual who's infected. So having too much iron is not good. It's a recessive condition. So that would mean you need to be Q squared to have this condition. We're told that 13,000 out of 1.2 million have it. So 13,000 out of 1.2 million have to be Q squared.
How many zeros are there?
6.
Okay, I always just like billion.
Where's that video camera when you need it? Okay, so what's Q? 0.1. So the allele frequency is 0.1 or 1, sorry, 10%. 10%. Okay. Two more.
Wait, sir, go back up
Okay, so we have two last questions left over. And then what we'll do is I want to wrap up that microevolution PowerPoint, which I just remembered that we didn't finish. No. Okay, so here, 1 in 2,000 babies are born with cystic fibrosis. The mortality age by 40 is 30%. What would the frequency of P and Q? Okay, so this is the type of question that could be the type of question I'm going to ask you, where it's actually more difficult than the other one because it's not that they're all sterile. 30% are sterile. Okay? No, it's easy. Trust me. So let's do this. 1 in 2,000 babies. So first off, let's figure out what Q is. So we know that 1 in 2,000 are Q squared. So we can go ahead and solve for Q. So what is that? What's Q? Go ahead. Tell me what Q is. 1 in 2,000, square root of that. What do you get? Okay, and therefore P must be, other than yellow, 0.98. Okay? Now, let's do the same thing I told you. Let's imagine a hypothetical population with 10,000 individuals. So let's do that, okay? We have 10,000 individuals. You don't need to do it this way, but this is, for me, this is easy. So we have 10,000 individuals. Sorry, I meant this is easier. Okay? 10,000 individuals. How many are P squared? So P squared would be 0.98 squared, right? So how many would be P squared? Well, you would expect it to be 0.98 squared times how many individuals we have. So P is 0.98. What's P squared? What's P squared? What is it? 0.9 what? 96. So what 96% of the population is P squared. So that means 96% of 10,000 is about 9,600. Oh, sorry, an extra, little extra zero there. All right. Now, Q squared. Well, we can actually do it two ways. We know 1 in 2,000. 1 in 2,000 would be the same as 5 in 10,000, right? But what's 0.02 squared? Should be not okay. And then, but we already know that this is 1 in 2,000. So 1 in 2,000 times 10,000 should be 5. No, 5. It's a simple ratio. If 1 in 2,000 have the disease, then how many would have the disease if we have 10,000? The ratio is still the same. Exactly. So we expect 5. I don't know. Now, what does that leave us with? That leaves us with 2PQ, which have to be, well, we know the population adds up to 10,000. So we have 9,600 plus another 5. That's 9,605. So this has to be 395. Okay? There's our population breakdown. If we have 10,000 individuals, 9,600 would be P squared, 5 would be Q squared, 395 would be 2PQ. Yep. Q squared is the... No, 9,600 don't even have the allele. Now this is where we have to think about the next generation. it says that, so in the previous example it was a little bit easier because we just actually eliminated who? We eliminated the q squared, right? But here it says that don't necessarily die. There's a 30% chance that they'll die. So it's still the same. What you do is you say, all right, well, let's say that 30% don't make it. What's 30% of 5? 1.5? So we expect, now I know this is going to be a little weird, but we expect 3.5 individuals will survive. Because 30% are going to die. So of the 5 babies, there's a 30% chance each baby will not make it. 30% of 5 is 1.5. You expect 3.5 to make it. Now you wait, how can half a baby make it? This is the statistics. It's not really half a baby, okay? Statistics. But now we can go back and do the exact same thing that we did before. We can say, okay, how many alleles do we have? So let's think about this. Yeah. No, because we're going to add it all up as a number, okay? So we have P. So here we have how many individuals? 9,600 plus 3.5 plus 395. What is that? Well, it's basically, if we add this all up, the total, right, it's only going to be off by, sorry, what did you say? 98.5, right? We should only have lost 1.5 individuals. Now, they each carry 2 alleles, so how many alleles is that in total? So what is that in total? Well, we lost 1.5 individuals, so we should have lost 3 alleles. So what is that? There we go. Let's pause this.
Pause your recording.
Go. All right. So let's finish this one off, okay? So we know, girls. So 9,998 and a half individuals are going to survive. Each has 2 alleles. Again, half an individual, just statistics, right? That represents 19,997 alleles. All you do now is you figure out what's the frequency of P. So my P allele, well, we know that 9,600 are P squared, and they have 2 alleles each. So that would be 19,200 P alleles in the P squared individuals. And then we have 395 are heterozygous. So they have 1 P allele each. So we add that up, and we get 19,595 P alleles. So that's the P allele. And then you do the same thing we did before. You figure out P allele over the total. We know the total is 19,997. What's your frequency? So this question is the same as the other one, but the other one we assumed that Q squared were all sterile. Here we assume that some of them, we can't assume that. Some of them will survive, right? 0.99. So what was it before? Before it was 0.98, now it's 0.99. So what must Q be then? Q must be...
Wait, you don't square root of that.
It's still 98? But it's probably... Because this is rounded off, right? So this could be 0.98, I don't know like what exactly it is, but it could be like 0.98000. This could, so you say it's still 0.98? This could be 0.98 3 something. Trust me, this has gone up, but it hasn't gone up much. Okay? It hasn't gone up much, but it has gone up. That's how you would calculate. It's the same method we did with this question here, but the only difference is not all of the q squared are going to be eliminated. Only some of them are. Not necessarily. Now, look at 8. 8. So you might think 8 looks exactly the same as 7, and you might think it's actually maybe even easier. On the surface, 8 looks like the previous example. 8 looks like this one, because it's saying that the recessive condition is sterile. Well, being sterile is the same as being dead. Why? Can't pass on your genes. So in this case here, it says there's a 1 in 100 in a million chance of having cystic fibrosis. So we do, okay, what's q squared? 100 over 1 million. There's our 6 zeros for Jessica. And we solve for q. So what's q? What's the square root of 1 over 1,000? 0.0 what? Is it 0.03? No. 0.03. 0.03? Okay. Maybe. What's p? Because it has to add up to what? Now, some of you may say, okay, look at this question. Okay, this is what I'm going to do. I'm going to assume a population of 10,000. And doesn't matter what number you pick. Because it's frequency. It's the same. I just use 10,000. Okay? And you can say, okay, what percentage are p squared? Right? And then you do, okay, 97% times, p squared is 0.97 squared times 10,000. And you figure out, but you don't have to do that here. You'd be wasting your time. Read the question carefully. Don't be tricked into doing something you don't need to do. So what year is this? 50s. Long time ago. So the reason why it's not the same scenario as the previous question is because we can assume that over time medications improve, higher chance of surviving. But this is saying that it's not really lethal until you're older. I didn't tell you that in the previous question. You can still have kids. So then we can assume that whatever P is, or whatever Q is, probably going to still be the same in the next generation. Because by the time it shows up, you would have already what? Had your kids. Same. Most likely it's going to be the same. Because whether you have, what this question is saying is, you're not going to really have the effect until you're older. But most kids are going to have their kids, especially in the 50s. You're not going to be waiting until you're 40 to have kids back then. You're going to have them earlier. So here, you don't need to worry about breaking it all down, and I would just assume in this case that the P and Q are going to be the same. Okay, ladies? All right. So that's it for the solutions.
Wait, can you not ask them with the document? Oh my god.